Hello, everyone. My name is Lei, and I'm a PhD candidate of structural engineering at the University of Alberta. The topic I'm going to talk about today is the analytical assessment on the timber concrete composite floors with discrete semi-rigid connections. Timber concrete composite floors, or TCC, is a composite floor system that combines a top concrete layer with bottom timber panels or beams. My research mainly focuses on the panel type TCC. TCC floors use the complementary material properties of timber and concrete. The mass timber panels at the bottom, such as CLT, DLT, and GLT, act both as stay-in-place formwork and the reinforcement of concrete to resist tensile forces. The concrete at the top is mainly subjected to the compression force. Of course, there are a lot of other advantages of this composite floor system, which I will not talk about in detail. The connection system between timber and concrete is often the governing factor for the floor performance. The picture on the right shows timber and concrete are connected with notches, which are made by cutting grooves on timber and then cast with concrete. But timber and concrete can also be connected with other types of connections. The most common connections are steel fasteners like self-tapping screws, coach screws, steel rods, and HBB connectors. My research mainly focuses on the notched connections. Compared with steel fasteners, notched connections are often more cost-effective. The notches are usually cut with a CNC machine in the fabricator's shop before the panels are sent to the site. This allows a faster erection of the floors compared with fasteners such as screws or steel plates, which can be time-consuming to install. The notched connections also have high stiffness and strength, which is beneficial for the floor structural performance. For the dowel-type fasteners, such as self-tapping screws, usually a lot of connections have to be used to achieve a certain composite efficiency in the floor. But for the notches, only several connections are needed to achieve the same level of composite efficiency. For this reason, the notches are usually widely spaced along the floor, and the timber and the concrete are discrete connected. But no matter which type of connection is used, the connections are always flexible in the composite floors, so they can only provide partial composite action to the floors. As you can see, the strings in timber and concrete are not continuous because of this partial composite action. The internal actions and the effective bending stiffness in a composite floor is determined by the composite beam theories. The most commonly used design method is the gamma method, which is included in Eurocode 5. But the gamma method assumes continuous bond between timber and concrete. As you can see in the expression of gamma, the connection stiffness K is divided by the connection spacing S, which means the connection stiffness is smeared along the composite floor. So the gamma method is best used for the continuous connections such as adhesive or closely spaced steel fasteners, but not necessarily for notched connections. Byfield proposed a release and restore method for the composite being connected with widely spaced connections. But in his model, the connections are assumed to be rigid, which means there is no relative slip at the locations of connections. The notched connections are not perfectly rigid, so the Byfield's method can lead to overestimation of the floor bending stiffness. Next, I'm going to talk about how to modify this release and restore model to account for the flexibility of the connections. This is a composite floor or beam connected with discrete connections. It could be notched connections or steel rods or other discrete connections. The first step of this method is to partition the composite floor according to the locations of shear connections. In each partition segment, timber and concrete is subjected to bending moments, shear forces, and axial forces. The internal forces cannot be solved directly since the system is statically indeterminate. Now let's introduce the release and restore method, assuming there is no connection between timber and concrete. So timber and concrete can slide without restriction, and there is no actual forces in timber and concrete. And then we restore the actual forces in timber and concrete caused by the shear connections. Concrete is under compression and the timber is in tension. But to maintain the equilibrium of this segment, the actual forces have to be eccentric about the centers of concrete and timber. Finally, the released and the restored segments should be combined to form the original segment. And then each segment should be combined to form the continuous beam. The relative slip should be continuous between adjacent segments. From this release and restore procedure, the internal actions in the composite floor can be solved. This method is not restricted to the connection locations and the stiffness or the external loads and boundary conditions. It can be used for any two-layer composite floor with discrete connections. I don't want to talk about all the equations from this method, but only three. Firstly, the equilibrium of bending moment in any cross-section is expressed by equation 1. If we can solve the actual forces in the segments, then we can solve the bending moments in timber and concrete. Once the bending moments in timber and concrete are solved, the deflection of the floor at any location can be solved from the more integral method, shown in equation 2. So how to solve the actual forces? For a simply supported floor, the actual forces can be solved from equation 3. The matrices and the vectors on the right-hand side of equation 3 are determined from the material properties of timber and concrete, the geometry of the floor, the connection stiffness, and the external loads. You can find the expressions of these matrices and vectors from my conference paper. So what this composite beam model can do? Well, except from determining the internal actions in the composite floor, this composite beam model can be used to optimize the composite floor design. So next, I'm going to talk about a parametric study on a composite beam connected with discrete connections. The factors I'm going to study are the relative thickness of concrete and timber, the connection stiffness, the number of connections, and finally the locations of connections. Since TCC floors are often governed by the serviceability limit states rather than the ultimate limit states, I'm only going to talk about the deflection of the floors. For comparison purposes, the calculated beam deflection is compared with the deflections of the full and the non-composite floors. The bending stiffness of the non and the full composite floors can be determined from these two equations. The first factor investigated is the relative thickness of concrete and timber. The relative thickness of concrete to timber is an early decision made in the floor design. The graph on the right shows the mid-span deflection of the floor changes with the concrete thickness, while the total thickness of the floor is maintained at 220 millimeters. From left to right, the thickness of concrete increases from 0 to the full thickness of the floor. When the concrete thickness is 0, the floor is bare timber. And when the concrete thickness is 220 millimeters thick, the floor is plain concrete. How the deflection changes with the concrete thickness is actually depending on the connection stiffness. When the connections are very flexible, the deflection of the floor increases first and then decreases. But when the connections are very stiff, the deflection almost monotonically decreases with the increase of the concrete thickness. A certain thickness of concrete in the floor can increase the thermal mass and decrease the acceleration of the floor under vibration. But a thick concrete layer can significantly increase the floor weight. As you can see in the graph, the weight of the floor linearly increases with the concrete thickness. When the connections have high stiffness, you can see there is a range. When the concrete thickness changes, the bending stiffness of the floor is almost constant. In this case, a thick concrete layer should be avoided. Now let's talk about the number of connections and the connection stiffness. It is quite obvious that the deflection decreases when the number of connections and the connection stiffness increases. When the connections have zero stiffness, the floor acts as a non-composite floor. But when the connections are perfectly rigid, the floor doesn't necessarily act as a full composite floor, especially when only a few connections are used. This is because the connections are discrete, so the relative slip is zero at the locations of rigid connections, but at other locations where timber and concrete are not connected, the relative slip can still exist. But when enough number of connections are used and the connections are rigid, the composite floor can be approximated as the full composite. Finally, let's talk about the locations of connections. Again, because the connections are discrete, depending on where the connections are installed, the floor can have different bending stiffness. As you can see from the graph on the right, when the connections move from the supports to the midspan, the deflection decreases first and then increases again. There is an optimal connection spacing for the floor to reach the minimal deflection. And this optimal spacing is not necessarily the same for different connection stiffness. Knowing where to install connections can be an effective measure to achieve the same composite efficiency in the floor, compared with increasing the number and the stiffness of connections. That's all I want to talk about today. For more information about this work, please refer to my conference paper. If you have any questions, you can send me an email. You are also welcome to visit our research group website and YouTube channel to find more information about mass timber research. Thank you and bye for now.